to record the lecture. So yeah, welcome to lecture 14 of Physics 1A, where we're still talking about rotational motion. Yesterday, we started talking about rotational motion by considering rotational kinematics. Kinematics, again, deals with how the object moves. So yesterday, we defined the angular displacement, angular velocity, and angular acceleration as kinematic variables that describe a rotating object. So today we will look at rotational dynamics. Dynamics, again, is looking at what causes motion or why the object rotates in the first place. We've learned about mechanical dynamics before when we talked about Newton's laws of motion, because we learned that if you apply a force on an object, if you push or pull an object, then this object can move. But we only looked at linear motion, like movement along a straight line. In this lecture, we will look at why the object rotates, what is the counterpart of force that will cause an object to rotate. So it's here, the counterpart of force is torque. So let's define torque. Torque is the measure of the effectiveness of a force to make an object rotate. So to make an object rotate, it's still force that's needed. Force being push or pull. And I'll just place this over here. Hopefully this is magnetic. In the center of mass. Right, so if I wanted to make this object rotate, then I would still need to apply a force being a push or a pull. If I push on this side, then I'm applying a downward force on this side, and the lever rotates. So it's still force that causes an object to rotate, but torque measures the tendency of that force to make the object rotate. It's the measure of the effectiveness of that force to make the object rotate. Or you can think of torque as a twist that causes an object to rotate. So for example, here you have a force and you push on the door, for example. Pushing on the door is applying a force, and that force will twist the door about some axis, causing it to rotate. Okay, so then, so just to define terms here, we will use this Greek symbol, which we read tau. Okay, so that's the Greek symbol tau that we will use to refer to torque. Okay, so we can see here from the definition of torque being the tendency to rotate an object, the torque will therefore create some angular acceleration. Yeah, we've defined what angular acceleration is yesterday. It's how fast the angular velocity changes, or how fast the angle changes over time. Right, so the counterpart of force will therefore be torque. When we were talking about Newton's law of motion, second law of motion, we were talking about the net force acting on an object that's causing the object to accelerate. So similarly, when talking about torques, then we also have to look at the net torque. Net torque being the sum of all the torques acting on an object that causes the object to rotate and have some angular acceleration alpha. Angular acceleration. Right? Okay, so how do we?
Sorry, just double checking the little symbol next to the acceleration means.
This alpha. This one, it means proportional. So it means proportional. Okay. So yeah, so the amount of torque is proportional to alpha. Bigger torque will give you bigger angular acceleration. Just like force, bigger force will give you a bigger linear acceleration. Yeah. Okay, so conceptually, this is what torque is about. How do we measure torque, or how do we determine torque? Torque is determined by the amount of force
exerted on the object. So this is force. Because for you to have torque, you also have to apply a force to rotate that object. So torque should be proportional to the force. It makes sense because if you push on this thing with a small amount of force, then you generate a small torque. If you push with a big amount of force, then you generate a big torque and you have a bigger rotation. So torque should be directly proportional to the force as seen in this equation. It's also directly proportional to some quantity called R. So what is this R? This R is called the lever arm or moment arm. Lever arm or moment arm is the perpendicular distance between the force and the point of rotation. Okay. The point of rotation, we call that as the pivot. So in this analogy here, if I apply a force downwards, the lever arm will be the perpendicular distance from the force, the downward force, and the pivot. So the pivot is the point where the object rotates, which is, the object rotates about this point. So this is the pivot. The lever or moment arm is therefore measured from the force to the pivot point. So in this case, this distance here is the lever arm R or moment arm R. So that's R in the equation. Theta, this is the angle between the force and the lever arm R. Okay. So theta becomes important when the force is not directly but perpendicular to the lever arm. If, for example, I apply a diagonal force, if I apply a diagonal force on this lever, okay, then there will be an angle relative to the moment arm and the direction of the force I'm applying on this thing. So that's when the angle becomes important. But ultimately, the lever arm or R should be measured perpendicular to the force. So say, this was what I was demonstrating earlier. If you have this force that's just vertically upwards, and this is the pivot, you measure the moment arm by extending this force. You can extend this force and you can draw a line from the pivot to that force so that that line is perpendicular to the force, so that this will be your lever arm RA or moment arm. Okay. And if you have a diagonal force, like you have this force FC that's exerted at some angle relative to here, then one way to find, there are two methods of finding the moment arm. One way is to extend the line of force so that you are able to draw a line that is perpendicular to that line of force and passes through the pivot. So this line defines the lever arm or moment arm. Okay. Right. So that's one way of determining the moment arm when the force is diagonal. The other way is to break down the diagonal force into horizontal and vertical components. And we already have been doing this a lot, and we're familiar with this. So any diagonal force can be broken down into its horizontal and vertical components. Notice how this vertical component is similar to this force on the left. Okay, so you can also extend the vertical force and you are able to draw this moment arm from the force to the pivot. Notice that for the horizontal components, the horizontal component will just directly pass through the pivot. So of course, you can just translate this horizontal component up here and draw that as FCX. And notice how the horizontal component will directly pass through the pivot. Any force that's not perpendicular to the pivot, say if I push on this thing in this direction here, assuming it's perfectly parallel to the lever and passes through the pivot point, will not create any rotation. Okay? So that means that the X component or horizontal component of FC will not contribute to the torque, to the torque. The key idea then is only the force perpendicular to the lever arm will contribute to the force. Okay. So then the equation for torque can just reduce to this, and this is probably the more common form of writing torque. It's just moment arm R times F, but I put the symbol here, which means perpendicular. To remind ourselves that you should get the moment arm perpendicular to the force, because only the perpendicular force will contribute to the torque. So you're welcome to use this equation, torque equals R times F, as long as you are measuring your lever arm perpendicular to the force. All right, any question how to get the lever arm? Because this is quite a crucial skill. Whenever we calculate torques, we have first to find the lever arm. And so if we are not able to find the lever arm, then we are not able to calculate the torque. But is that clear enough so far, how to find the lever arm? Yeah, we'll look at an example to apply these things. But before we look at the example, let's just define the the directions of the torque. So when we were talking about force, we defined positive force and negative force, being if you push to the right, we took this as a positive direction, push to the left, negative direction. For torque, because torque rotates the object, let's define some convention. If the tendency of the force is to rotate the object anti-clockwise, then the sign of the torque will be positive. Okay, and if the tendency of the force is to rotate the object clockwise, then we assign a negative torque in that case. Okay. All right. So here, if I push in this way, the force will cause this thing to rotate anti-clockwise. So will this be a positive or negative torque? Positive. Yeah, anti-clockwise, positive torque. Whereas if I push on the other end, the tendency of this force will be to rotate it in the clockwise direction, so that will be a negative torque. Yeah. Okay. All right. So then let's look at this example here. There are three forces applied on this wheel. The wheel has a radius 0.30 meters. The forces are as shown. You have 11.9 newtons directly downwards, 8.5, 50 newtons upwards on the rim. And you have this 14.6 newtons that's like pulling at some angle 40 degrees. We want to find the net torque on the wheel. So torque is defined as the lever arm that's perpendicular to the force. So to find the torque, we need first to find the lever arm. So this exercise, this example is actually all about finding the lever arm because all the forces are given. Right. So we want to rotate the wheel about this. It says we want to rotate the wheel through its center. So this will be the pivot. Right, so if we extend the 11 Newton force to pass through the pivot, notice how the force just directly passes through the pivot. So there's no way for us to draw there's no way for it to be perpendicular, draw a line that's perpendicular to this force and passing through the pivot. Yeah. Right. So the moment arm for the 11.9 Newton force should be 0. You agree? Right. So the 11 Newton force just directly passes through the pivot. Yeah, there's no way that we can draw a line that's perpendicular to this 11.9 Newton force. Right. For this 8.5 Newton force, we can draw this line. It passes through the pivot, and this line is perpendicular to the 8.5 Newton force. Therefore, this will be the moment arm for the 8.5 Newton force. Yeah.
So if it's not perpendicular, you can't have a
moment arm. Yeah, you can't have a moment arm. So like here, if you apply this force in this direction, you can't have, there's no moment arm here. The moment arm will cause, essentially, it's that orientation where you need to apply the force to generate a rotation.
It doesn't have to be just 90 degrees.
It doesn't have to be 90 degrees like here, or if I push in this direction, I can still make this thing rotate. Because any diagonal force will have a component that will be 90 degrees to this. And what we want to find is that component that's 90 degrees to the pivot. I mean, yeah, that will pass through the pivot and 90 degrees to the force. Yeah. So just like this 8.5 Newton force here, we can draw this line that's perpendicular to that force, which defines the moment arm in this case. Then the force is at the rim of the wheel, so the moment arm will therefore be just the radius of the wheel. Right, how about now let's look at this 14.6 newtons. It has 40-degree angle here. Maybe I'll just use a clean drawing, or maybe I'll use a different color. Okay, so the technique here will be to extend the force, so that extending this force this way, the moment arm should be 90 degrees to the extended force and perpendicular to the extended force. Let me try to draw something perpendicular like this, right? Okay, so if I draw the blue line that's perpendicular to the extended line of force, this will be the moment arm for the 14.6 Newton force. Okay. It passes through the pivot and it's perpendicular to the force. This dashed line here is just the extension of the force. It's necessary to extend the force for you to see, where you can draw this line that's perpendicular to the force. But then you can see here that if this is 40 degrees, then this will also be 40 degrees. So the moment arm here will be a sine theta function of, yeah. So the R of 14.6 Newton will be the 0 point sine 40 degrees, isn't it? So the radius here, 0.35 meters, that is the hypotenuse of the right angle triangle. The right angle triangle consists of the moment arm over here, the line of force, and the radius of the wheel. So the moment arm here, this side, will be 0.35 sine 40 degrees. Is that all right? Do we follow up to this point? Okay, so now we have our moment arms. Yeah, so let me just use a clean page. So we write it, the torque, net torque will then be equal to the torque due to 11.9 newtons plus the torque due to the 8.5 newtons plus the torque due to the 14.6 newtons. Okay. Right, torque is moment arm for the 11.9 newtons times the force, plus the moment arm for the 8.5 newtons times the force 8.5, plus the moment arm for the 14.6 newtons times the force we have there. Okay, we've determined the moment arm here is 0, so that will be 0, plus the moment arm for here, we've determined this to be 0.35 meters, so that's 0.35 meters times 8.5 newtons. Okay. Plus the moment arm here, we've extended this, and this is the moment arm. This will be 0.35 sine 40 degrees times the force 14.6 newtons. That's in meters. All right, so net torque is like this, but then you also need to consider the signs of the torque, right? You have to consider the first one, you don't have to worry about because the torque contributed by this is 0. For the two forces here, which force will give you a negative torque and which force will give you a positive torque? Will the, so let's look at the 8.5 Newton force. Will this give a positive torque or a negative torque? Positive, because it will rotate this in the anti-clockwise direction, whereas for this force, the tendency is to rotate it in the clockwise direction. Hence, this one should be negative instead of positive. So your net torque finally will be negative 3.285 newtons times meters. All right, any question about?
That's just the value for the 14.6.
Oh, I didn't, yeah, they didn't add it. Sorry, yeah. This is just for the 14.61. So yeah, finally, this one 2.975 plus negative 3.285. All right, So we've now defined the counterpart of force. Force in rotation becomes torque. Now, yeah, of course, acceleration becomes angular acceleration. External force becomes net torque. Now, what's the counterpart of mass? Okay, so the counterpart of mass, the mass, we've defined this as the inertia of the object. And when we say inertia, it's the resistance to changes in motion. It's the tendency to resist changes in motion. So to find the counterpart of mass, what is that thing that resists rotational motion? Okay. That thing that resists rotational motion is what we call moment of inertia or rotational inertia. We use the symbol capital I for rotational inertia or moment of inertia. So the moment of inertia will depend on the mass of the object. If you think about it, the more massive, the heavier the object is, the more difficult it is to rotate this object. It also depends on the distribution of the mass around the axis of rotation. So these figures here illustrate this point. If the masses are at a farther distance from the axis of rotation, it's more difficult to rotate that object. So how do we find the moment of inertia or rotational inertia? It should depend on the mass and the distribution R. So given a set of masses, say as shown here, you have two masses here, the moment of inertia of this dumbbell is equal to the mass at one end times the distance of that mass to the point of rotation. Yeah, and then there's a square there, plus the mass at the other end times the distance from the point of rotation squared. And you do this thing for every mass present in the system, or in this is just the short notation. It's the sum of the mass times the distribution squared, or distance from the axis of rotation. Okay. So moment of inertia, it resists rotation, rotational motion. It then follows that if you have a small moment of inertia, that means that it's easier to rotate this object. And so a small moment of inertia can give you a larger angular velocity, whereas a larger moment of inertia gives you a small angular velocity. Okay, for some extended objects, the moment of inertia moments of inertia can be looked up at a table. So for these particular extended objects here, you can just use this slide to work out what the moment of inertia is. But notice how each moment of inertia still depends on the mass. So M is still the mass, and R is some distance from the rotational axis. So if this is the rotational axis, in the middle, R is still the distance of the mass from rotational axis. Right. So for some systems, you don't have to determine the equation for the moment of inertia. We're happy for you to look at this table to find the moment of inertia. If the objects are discrete masses, like here, then you find the moment of inertia from this equation, right? So those are, yeah, two ways. What I will point out here is, let's look at these two rods. There's one rod here. The axis of rotation is at the middle of the rod. This other rod here, the axis of rotation is chosen to be at one end of the rod. Notice how the equation for the moments of inertia of these two rods are different. This just illustrates that the moment of inertia is not unique. It depends on the axis of rotation. So there is this parallel axis theorem gives us a way of determining what's the moment of inertia if we change the axis of rotation of the object. The parallel axis says that the new moment of inertia is equal to the moment of inertia through the center of mass. Moment of inertia through the center of mass plus the moment of inertia at the new axis, okay, where m is the total mass of the system and h is the distance between the two axes. So how do we apply the parallel axis theorem? Let's look at this example. This is the rod. The moment of inertia, if we rotate this rod through the center of mass, which is at the geometric center, is 1/2 times the total mass times the length of the rod squared. What will be the new moment of inertia if we move the rotation axis at the at one end of the rod? Okay. So parallel axis theorem says that the new moment of inertia, so this is the new moment of inertia at an axis that's parallel to the original one, is equal to the moment of inertia at the center of mass, which is 1/12 ml squared, plus the mass times h is the distance of the new axis to the center of mass. So this was the original center of mass axis. The distance between the center of mass and the new axis is L/2, right? Because the center of mass is at the geometric center, and now we want to move the axis of rotation to one end of the rod. So then that will be L/2 squared. Right. So the new moment of inertia will therefore be one-third ml squared. Okay, so up to this point, we were just defining different terms, right? We first defined what torque is, being the counterpart of force, and then we learned how to calculate the net torque by finding the lever arm. And then next, we defined moment of inertia to be the counterpart of mass, and we learned how to find the moment of inertia either of different masses. For different masses, we find m1r1 squared, and we add this together. Or for shapes, for defined shapes, we have defined moment of inertia equations. If we change the axis of rotation for these defined shapes, we can find the new moment of inertia using parallel axis theorem. So far what we've defined are the different variables that we need to define rotational dynamics in the same way that we defined translational dynamics with Newton's laws of motion. So to put everything together, the angular acceleration, if we write down Newton's second law of motion for rotation, the angular acceleration will then be proportional to the net torque and inversely proportional to the moment of inertia. So Newton's second law of motion for rotational motion is net torque. Okay, so this is just simply net torque. Sum of all the torques generated by the forces acting on the system is equal to the moment of inertia times the angular acceleration. Okay, right. So after defining this, let's just compare translational motion and rotational motion. The measure of inertia or resistance to the changes in translational motion is defined by the mass. Resistance to rotational motion is defined by rotational inertia or moment of inertia I. The cause of change in motion for translational motion, force causes an object to move along a straight line. Torque causes an object to rotate. Okay, how we write Newton's second law of motion, net force or sum of all forces equals mass times acceleration. Net torque in rotation, net torque is equal to moment of inertia times angular acceleration. And in the next lecture, we will talk about kinetic energy. In translation, it's 1/2 mv squared. In rotation, 1/2. Mass is equivalent to moment of inertia. Velocity is angular velocity. Right? Okay, so all the techniques we've learned before will apply, drawing the free body diagram, taking the net torque, and all of these things. You can use them here. And so let's just look at this example to bring everything together in terms of rotational dynamics. So you have a pulley. The pulley is here. It's used to lower corn cobs for disposal. The waste load, this is the waste load. Here, it exerts a tension force of 25 newtons. So, so you have this tension force here, 25 newtons to the rope. The rope is wrapped around the pulley of mass 5 kilograms. The radius of the pulley is 0.35 meters or 35 centimeters. The pulley accelerates from rest until an angular speed, a uniform angular speed of 40, sorry, not a uniform angular speed, but it accelerates to an angular speed of 40 radians per second in 4 seconds. There's friction. The frictional force in the pulley provides a frictional torque of 1.20 Newton meters. So the torque due to friction is already provided 1.20 newtons times meters. We want to find the moment of inertia of the pulley.
Why is the friction drawn in that direction? Wouldn't it be perpendicular to or opposite to the direction of rotation?
Yeah, so the friction, the frictional force will cause a rotation that will be perpendicular to the rotation. You're correct.
Okay.
But the force, so the force can be in any orientation as long as the tendency is to rotate in the opposite. So if the pulley is rotating in the anti-clockwise direction, your frictional force should be drawn such that the rotation will be in a clockwise direction. So yeah, so this is just the chosen orientation. You can draw frictional force in this direction as well.
Yeah, but if you're drawing it perpendicular to the center, then you'd say you'd ignore it because it's going to the center.
Because like the
Yeah, so this seems long to draw through the center, like perpendicular to the center would not have any effect on the rotation if it was a force in that direction.
right, because the moment arm, you
Yes.
were saying the moment arm. Yeah, that's a yes, that is a good point. So yeah, so the friction, yeah, should have moved at somewhere here, not through the center. Yeah, good point. Okay, so let's look at this. Let's use the strategy we used before in forces. draw a free body diagram, well, the forces are already drawn for you. Usually that will be indicated. So let's write down what's given. The tension force, this is 25 newtons. Okay. The radius 0.35 meters. We are given a initial angular velocity. So the pulley rotates from rest. So that's an initial angular velocity of 0, right? It rotates to 40 radians per second. That gives you a final angular velocity of 40 radians per second in a time of 4 seconds. Okay. The frictional torque is already given. Torque due to friction, 1.20 newtons times meters. Okay. We want to find the moment of inertia. Right, so if the pulley can be considered to be a sphere, then you can use the moment of inertia equation for a sphere, except that you don't know the mass of the pulley, right? So you can use the table in the slide I showed you with the equations of moment inertia for different shapes. But in this case, that's useless because we don't know the mass of the pulley. So the only other way to find the moment of inertia is to find the net torque. So the net torque will be equal to the moment of inertia times the angular acceleration, right? Newton's second law of motion for rotation. So for us to find the moment of inertia, we need to find two things. We need to find the net torque and we need to find the angular acceleration, right? Okay, so let's find the net torque first. So find net torque. Maybe I'll just use the next page because it's going, I'll just use a new page. So find the net torque. Okay, this will be, there are only two forces here, the tension force and the frictional force. So this will be the torque contributed by the tension and the torque contributed by the friction, which will give a positive torque, the tension or the friction. Yeah, tension, the tendency for tension force is to pull the wheel in the anti-clockwise direction. So the torque for tension will be positive, whereas the tendency for friction is to oppose the rotation. So that will be a negative torque due to friction anyway. Right. So torque due to tension will be the moment arm. So you have your tension force that's downwards, the moment arm through the pivots will just be the radius of the pulley. Right. So this will be, so recall that torque is equal to moment arm times the force. The moment arm for the tension is 0.35 meters. Okay. Times the tension force is given 25 newtons. Minus the frictional torque. The frictional torque was already given as is. So we just use this one, 1.20 Newton meters. Right, so this gives us a net torque of 7.55 Newton meters. Okay, next thing we need to find is the angular acceleration. Find the angular acceleration. Right, what do we know? We know the initial angular speed is 0, it's from rest, and the final angular speed is 40 radians per second, and the time is 4 seconds. Right. So the only way to find angular acceleration in this case is to use the kinematic equations for dynamics, isn't it? Yeah. Right. So I haven't listed it down, but you can refer to the slides. We have there the relationship. Sorry, omega naught times final angular velocity equals initial angular velocity plus alpha t. Yeah. Initial angular velocity is 0, therefore we can find angular acceleration, final angular velocity over time, which we already know. So alpha is equal to 40 radians per second divided by 4 seconds. Ten radians per second squared. Okay. Right, so we know net torque. We've calculated the net torque. We've calculated the angular acceleration. Then we can find the moment of inertia from Newton's second law of motion for rotation. Moment of inertia of the wheel will therefore be the net torque divided by angular acceleration alpha. Net torque was 7.55 Newton meters divided by 10 radians per second squared, 0.755 kilogram meter squared. If you want to check the unit for moment of inertia, you can expand. Newtons is kilogram meter per second squared. So this one, if you expand the units, you have kilogram meter times meter divided by second squared times second minus 2, right? And so that will give you a kilogram meter squared for the moment of inertia, for the unit of moment of inertia.
Second in yes.
M squared, sorry. Yeah. Cool, any question about the solution for this problem? Okay. All right, so I'll leave you with this exercise, which came from a past year's test, and you can try this whenever you want. I'll post the solution on stream, but essentially this ends our lecture on rotational dynamics. Yes. And tomorrow we'll learn about rotational energy, kinetic energy.